keeping the same geometry, that's the flat plate, we now want to move on to the situation of natural convection and talk about what formulas to use and so on. But before that, we should get a better picture of what natural convection looks like. So in the next video, you are going to see two things side by side. On the left is the actual flow visualization, like we have seen before, of the neutrally buoyant bubbles rising. On the right is computation. That means solving the set of equations of flow and heat transfer. They both kind of try to visualize exactly how the flow happens. So please observe carefully. So here is another example. We will see contrasting natural convection with forced convection. So what you see now is forced convection, and it's airflow over human head. The air is flowing with some bulk velocity of u infinity. Now, by contrast, on the right one, air is moving not because of any forced flow, but simply this the surface of the skin is warmer. That heats up the air next to it, and heated air is lighter, so that air moves up. Okay, this is easier to see in a animated situation, so you can see how the air is flowing. Okay, but this flow is not because of some velocity that's forced in there. It's simply because of the temperature difference between the skin surface and the surrounding air. So then it's kind of hard to talk about Reynolds number. So in this case, we talked about we could talk about Reynolds number because we know u infinity. Here, the velocities are actually 0 on the surface and 0 far away. So 0 on the surface and 0 far away. In between, it has some velocity. But that velocity really depends on the temperature difference. So since there is no forced velocity, it's kind of hard to talk about Reynolds number. So we do not have any Reynolds number in there. So Reynolds number is not going to work in this kind of natural convection very effectively. We will see what number replaces Reynolds number, but I want you to see that the forced velocity here, u infinity, is 0, and that's why the Reynolds number is not going to work. So now we dig deeper into what parameters are driving this natural convection. So as you can see in here, if the air has to flow, its density has to change, meaning when heated, its density has to change. So how the density change with temperature is for the fluid, that matters. So density change with temperature is one of the factors. Then higher the temperature change, the more is the density change and easier for the fluid to flow, so the amount of temperature change matters. Then if there is no gravity, if we are doing this in space, then even though the density changes, it doesn't have to go up. So gravity has to be a factor in this process. Then finally, or another factor would be viscosity. If it is very viscous, it's not going to flow as easily. So all of these factors we can show through analysis that we can capture all of them into this one parameter. And that parameter is the Grashof number. So again, there is no forced velocity, u infinity, so no Reynolds number. Instead, this number captures all of them. So this beta is the density change with temperature. We will look at the units later on. Then we have the gravity. This is L is the characteristic length. Delta T is the temperature change as we discussed. And then nu is mu over rho, where mu is viscosity and rho is the density. Okay, so these are the fluid parameters. So everything is captured in this Grashof number, and this number will replace Reynolds number, because Reynolds number is not very useful because we don't have this forced velocity. So in natural convection, then we're going to use Grashof number, or the correlations or the equations for H will have Grashof number in them. So back to our slide of list of non-dimensional numbers. So we just saw one more, that is the Grashof number that got added to this. And then because Grashof and Prandtl are often together, then there's also one defined called the Rayleigh number, which is simply Grashof times the Prandtl number. We don't have to spend too much time on this right now. We'll simply we'll see this in our formulas, so then we know how those are defined. So when you see this in the formula, you come back here and you see this is how Grashof number is defined, or this is how Prandtl number is defined. And so here is yet another fun example of the effect of natural convection. We are used to seeing a candle burn this way. That's the left figure. This has to do with the heated gases from combustion flowing up due to gravity. If gravity were not there, as it would be, for example, in the space station, then there is no moving up of the gas, and the heat will move and the hot gases will move outward symmetrically, and so you will get this kind of a more of a symmetrical spherical shape on the right. So as you see from this candle burning, natural convection is everywhere. Because in natural convection, the fluid is heated from the surface and it rises up, so there is kind of a direction of flow. So the orientation of the heated surface, as you can expect, it makes a difference. This is what is shown in the two visualization, in the visualization following this slide, if for the two cases. And the two cases are, it's the same hot plate that you have seen before. It's the same one that is used for cooking. And on the left is the heated side facing up, which is normally how we would use it. So the surface is, the top surface is hot. On the right, this is not how we use it, but for the sake of making the point for the sake of understanding natural convection. We hold this same hot plate with the heated side facing down. So you can see me holding this hot plate here with the heated surface facing down. Ts is the surface temperature and T infinity is the surrounding fluid temperature. So with this heated side facing up here and heated side facing down here, can you guess whether the flows would be any different? Or if I give you a hint, where would the flow be faster? The equations for H that are also superimposed in here, that should give you a hint which way you would find a more flow or a higher H. So here we have a collection of all the formulas for natural convection. On the left are the formulas when the plate is horizontal, and on the right is when it's vertical. So in the horizontal position, then the two cases that we saw are heated surface facing up and then heated surface facing down. Okay, so for those two situations, A and B, the formulas are this one and this one. So you notice that this coefficient is lower. So for B, it is going to be lower than A. If we write out this equation, Nusselt number L is HL over K of fluid is equal to 0.54 times this Grashof number times Prandtl number, which we can figure out based on all the parameters given. So the point is this 0.27 is lower than 0.54, which means the H value calculated is going to be lower for this, which is what we expect from those flows that we see, because the flow is kind of restricted. When you heat the air here, it goes lighter, then it tries to go, but it can't. There is no way to go, so it kind of divert and move sideways. That becomes a slow process. So the H is lower. So you want to, when you see the formula, you don't want to just use the formula. See if it does make sense. Then the next thing is, instead of a heated surface, so of course we can have a colder surface, and the opposite will happen. So here the surface temperature is less than T infinity. So the cold air, when the air is cooled, it drops. So it sets up flow like that. And so the two cases that are equivalent are when the heated surface facing up or the cooler surface facing down. So this is a cooler surface facing down. These two are equivalent. So for A and D, we have the same formula. Likewise, for B and C, we have the same formula. Okay, so that's about horizontal position of the plate. It can also be, of course, vertical position, and then for vertical position we have this formula, It looks complicated, but realize that it's nothing but plugging in. So Rayleigh number is Grashof number times the Prandtl number. So we simply plug in. That's all. And NUL is HL over K. So if you plug in everything, then we get H. That's how we use them.